Bom, boa tarde. Continuaremos agora com a última parte do mini curso, que trata sobre a reatividade de contínuos da chalcona e ciclo chalcones, análogos do ciclo chalcones. Ministrado pelo professor Perieschi, da Universidade de Pest, da Hungria. Esta parte terá aproximadamente uns 40 minutos por aí, e é a última parte do curso. Então, vou passar a palavra para o professor Perieschi. Espero que tenha um bom final do curso. Muitas graças, muito obrigado por assistir o curso. Estou dando desde agora e espero que todos tenham gostado do curso. Começando, já o professor Perieschi vai começar.
As a result,
you need to begin. The people then you need to come back and begin, please.
okay, just. So welcome to the last unit of this mini course on chalcones and chalcone analogs. This session will discuss some aspects of the reactivity of chalcones and their cyclic chalcone analogs that, as it will be shown, has got biological importance in connection with their pharmacological, toxicological, biological activity of the chalcones and their derivatives. In this session, similar to the previous ones, 4 series of a set of chalcones and chalcone analogs will be involved. I mean, reaction of thiols with the open chain chalcones, the 5-membered ring chalcone analogs, the 6-membered ring chalcone analogs, and the 7-membered ring chalcone analogs, as described as whose synthesis and configurational specification has been published in the references mentioned in this slide. Because the thiol reactivity affects the carbon-carbon double bond of the compounds, the stereochemistry of the chalcones and the cyclic analogs plays an important part in these particular reactions, especially important part in these particular reactions. As I mentioned to you, in most cases of the open chain chalcones and in all the cyclic chalcone analogs, the configuration of the carbon-carbon double bond is E, and the configuration of the sigma bond is S-cis. So this is the starting 3-dimensional structure, which is involved in reactivity in interaction of the chalcone molecules and the nucleophilic reagents. Simplifying the essential of the reactivity of chalcones and other enones towards nucleophiles, we can describe the reaction as a result of formation of a covalent bond formation between the beta carbon atom and the nucleophilic atom of the reagent, using up its lone pair of electrons, and after in the second step, protonation of the intermediate to form the neutral adduct. The mechanisms of them, however, sometimes more complicated. What is the importance of reactivity of chalcones with nucleophiles, particularly the reactivity with thiols? The importance, this reaction is important because of the biological relevance of the reactions, namely those compounds which can bind to an active site of an enzyme, active site of a receptor. After binding to the active site by non-covalent interactions, in case of available and reactive thiol functionality, and in case of reactive center of the foreign substances, covalent links can be developed between the biological target and the foreign substance. As a result, the primary structure of the target molecule has been modified. And as for the biological relevance, it could be metabolism of the foreign substance when the foreign substance, for example, reacts with glutathione. In the glutathione as transferase catalyzed reaction or spontaneous reaction. And there are several biological effects which results from covalent modification of cysteine residues, the targeted covalent modifications. Among them, we can mention the inhibition of protein kinases which results in anti-tumor effect of the compounds. For example, inhibition of the NF-kappa B pathway, which results in anti-inflammatory effects, activation of the NRF2 pathway, resulting in anti-tumor cytoprotective effect, or interaction with tubulin, which is considered to be also considered to be the covalent modification of the active sites of the tubulin polymer. When we take into consideration of the thiol reactivity of chalcones, we should take into consideration two different pathways. The most commonly described and considered pathway is reaction of the deprotonated thiol nucleophile with the target chalcone molecules. As a result of such reaction, using up the lone pair of the deprotonated nucleophile, a covalent bond is formed, and at the same time, a negatively charged anion is formed, whose negative charge typically localized in the oxygen, resulting in an enolate intermediate. This enolate intermediate in the next step is under protonation, resulting in the product, the neutral product, generating one chiral center. The other possibility is the reaction of the chalcone molecule with the protonated form of the thiol, which is a neutral form of the thiol nucleophile. In such a situation, as a result of the first step, formation of the intermediate, a Zwitter ion is formed, resulting in a negative charge on the enolate moiety and a positive charge on the nucleophilic atom in the nucleophilic sulfur atom. Afterwards, in intramolecular proton transfer, the final product is formed, which is structurally very much the same as it forms in the previous path, reacting the deprotonated nucleophile. In this case, also in case of non-chiral nucleophilic reagent, one chiral carbon atom is formed. In our experiments, we used N-acetylcysteine and glutathione as model thiols under different acidic conditions. We chose three different conditions for our experiments, namely pH 8, pH 6.3, and pH 3.2. We chose pH 8 because this pH mimics the milieu of the glutathione S transferase catalyzed reactions, in which the thiol, the deprotonation of the thiol is increased with the tyrosine phenolic hydroxyl interaction of the glutathione, and that's why the rate of the reaction increasing. The pH 6.3 conditions were chosen because the pH of the cancerous cells are reported to be slightly more acidic than the normal cells, and that's why we performed the reactions under such particular conditions as well. The third one, the pH 3.2 conditions were chosen to exclusively to investigate how the protonated form of the two thiols is formed, since under such conditions the percent of the deprotonated form is practically zero. Before we go into the details, let's have some words about the stereochemistry of the reagents and the stereochemistry of the products. As it was mentioned, the stereochemistry of the chalcones we have already discussed. As for the stereochemistry of the glutathione, as you can see, the glutathione itself as a tripeptide carries two chiral carbon atoms, and both chiral carbon atoms are enantiomerically pure, so the natural glutathione is a pure enantiomer. When the natural glutathione is added onto the open chain chalcones, one new chiral carbon atom is formed. It means, as a result, the reaction results in formation two diastereomeric adducts, which only differ in the configuration of the newly formed chiral carbon atom of the beta carbon of the chalcone molecule. Under all HPLC conditions, that we use to investigate the progress of the reactions, however, the two diastereomers were not separated in case of glutathione. Only in the case of an acetylcysteine. So, in case of the glutathione reactions, we were able to follow how the area under the curve of the starting chalcone molecule is decreasing as the reaction proceeds. Here are the curves describing the progress of the reactions with some selected open chain chalcones. For example, in chalcone referred number 1, okay, were investigated with glutathione under pH 3.2, under pH 6.1, under pH 7.4, and under pH 8. As we can see, as the pH increasing and the portion of the deprotonated glutathione molecules increasing, the reactivity, the initial reactivity of the compounds is increasing. This was observed in both compounds, both hydroxyl substituted compounds with two different substituents on the benzylidene moiety. In another set of experiments, we compared the reactivity of another chalcones, which have got different substituents in the benzylidene moiety, namely chalcone A and chalcone B, having a methyl and a methoxy substituent. When we performed the reaction under pH 8, we could see that similar to the previously investigated open chain chalcones, the initial reactivity of the two chalcone compounds is very high, and in practically in 50-60 minutes, almost the whole amount of the chalcone is converted into the final products. When we decreased the pH, under pH 6.3, the initial reactivity was not as fast as in the case of 8, and the difference in the reactivity of the methyl and the methoxy substituents, the methyl blue and the methoxy orange substitution, became more evident. What we could see that the initial reactivity of the methyl substituted derivative is higher than the methoxy substituted derivative. When we further decrease the pH, the similar difference in the reactivity of the two derivatives were still observed, namely the methyl substituted derivatives got some higher initial reactivity than the methoxy, and as we can see, the rate of the reaction is much lower than that observed under any of the other pH conditions. When we performed the similar reaction with N-acetylcysteines, we were obtained very much the same graphs. Okay? Namely, the reaction were very fast under strongly basic conditions with higher reactivity of the methyl derivatives. The initial reaction was lower and under the pH 6.3 conditions, with the methyl derivatives being the more reactive again, and you can see the reactivity of the compounds with N-acetylcysteine were rather low in this model thiol as well. When we were analyzing the stereochemistry of the products, and just a minute, I go back to recall the two possible products. Okay, the two diastereomeric products in case of GSH reactions were not separated. However, it was separated in the case of the reaction with N-acetylcysteine. Based on the peak areas of the N-acetylcysteine adduct with the shorter retention time and the higher retention time, I mean the more polar and the less polar adducts, we could see that under pH 3.2, in both cases, but in particular in the case of the methyl substituted derivatives, the amount of one of the diastereomer were much higher than that of the other. When we increase the pH, such a high diastereoselectivity was dropped in both cases. When we were thinking about the high stereoselectivity of the adducts formation under the strongly acidic conditions, we considered formation of a hydrogen-bound stabilized six-membered ring intermediate, whose conformation is determined by the preferred orientation of the bulky aromatic ring. And that preference of the bulky aromatic rings determines and gives preference formation of one of the adducts in one of the diastereomeric adducts, which is reflected in the ratio observed under the strongly acidic conditions. In another set of experiments, we were investigated the thiol reactivity of the bis-Mannich derivatives of the the previously mentioned hydroxyl substituted chalcones. The bis-Mannich derivatives carries two additional nucleophilic sites, two nitrogen atoms, which under physiological conditions or under the conditions we have investigated, partly or exclusively exist in protonated form. So we have seen and we have investigated how the pH affects the initial rate of the Mannich derivatives. We observed very much the same tendency, namely the reactivities were found the lowest under the strongly acid conditions, under which or modal thiols were existing in protonated form, and as the pH was increasing, the initial reactivity was increasing in both cases. When analyzing the distribution of the diastereomic distribution of the adducts, we could see that the open chain chalcone, the non-Mannich chalcones, did not show any diastereomic selectivity. However, when we were seeing the diastereomic distribution of the adducts, the glutathione adducts of the bis-Mannich chalcones, under acidic conditions, pH 3.2, we saw again a relatively high diastereomic excess of one of the diastereoisomers. And this selectivity was only observed under the acid conditions. These are the HPLC chromatograms at this of the incubation mixtures, showing the 0 minute or 55 minutes with high amount of the initial chalcone and low amount of the ducts, and in the end of the reaction, when we can see formation of the two diastereomic adduct with somewhat higher amount of the less polar derivatives and substantial decrease of the initial chalcone. We gave explanation that we expected to form an ion pair, formation between the protonated nitrogen atoms and the deprotonated carboxylate functionality of the glutathione, and this ion pair formation gave a preferred preferred side of attack of glutathione of the beta carbon atom. In the next series of reactions, we started to investigate the effect of incorporation of cyclic moiety into the open chain chalcone structure. Initially, we started to investigate the pharmacologically more prosperous derivatives, the 7-membered ring derivatives, again choosing the methyl substituted and the methoxy substituted compounds. When we performed the reaction under acid conditions, strongly basic conditions, that we could see that both compounds, I mean the 1A, I mean the open chain, and the 1B, methyl and methoxy derivatives reacted very fast as we expected. However, when we were analyzing the reactivity of the cyclic chalcone analogs, we could see that the reactivity, the initial rate of reaction in case of the ring of the cyclic analogs were much lower. So it means that introduction of the ring structure into the open chain structure reduced the reactivity of the beta carbon. While investigating the possible reasons of this lowering of the reaction, we compared the carbon 13 NMR delta values of the beta carbons, the carbon number 10, in case of the open chain compound and the 7-membered analogs. As you can see, the carbon 13 chemical shifts are indicative of the electron density around the particular carbon atom. Here we can see fairly substantial differences between the chemical shifts values, indicating that the electron density around the beta carbon of the cyclic analogs is much higher than that of the open chain chalcones. And as for the other approach, these reactions were also analyzed based on the hard soft acid base theory, and the HOMO and the LUMO energies were calculated in case of the first and in case of the open chalcone and the 7-member chalcones. When we were calculating the HOMO LUMO, I mean the highest occupied molecular the difference between the HOMO of the protonated and deprotonated thiol and the LUMO of the chalcones, we could see that the difference between them is again shows characteristic differences. Namely, in case of the open chain chalcones, these two energies are closer to each other than the other, which is also predict a higher reactivity of the open chain chalcones in comparison with the cyclic ones. When we investigating the cyclic chalcones reactivity towards glutathione and acetylcysteine, we are facing a somewhat more complex stereochemical challenge. Namely, when the glutathione, for example, is added to the beta carbon, besides the chiral carbon atom of the beta carbon of the original chalcone, another chiral carbon atom is formed. The alpha carbon is also became a chiral center. As a result, altogether there are 4 chiral carbon atoms in the product, which theoretically allows formation of 8 different enantiomers, or 4 different enantiomer pairs, diastereomer pairs, sorry. When we were investigating the reactions, however, only 2, not 4 diastereomeric peaks, however, only 2 diastereomeric peaks were observed. At the moment, unfortunately, we do not know, because we do not know the absolute stereochemistry of the ducts, we do not know which 2 diastereomer comes together with shorter retention time, and which 2 comes together with somewhat higher retention time. Mass spectrometric analysis proved their structure. The stereochemical analysis is to be solved in the future. What we could see based on this information, what we could see that the ratio of the HPLC peak areas of the GSH conjugates is about 1, so no diastereo selectivity were observed under pH 6.3 and pH 8 conditions. Under pH 3.2, no reactivity was observed in the cyclic with the cyclic chalcones. When we were analyzing the composition, I mean the diastereomeric distribution of the N-acetylcysteine ducts with different retention times, we were seeing some diastereo selectivity above under pH 8, and the expectedly very high diastereo selectivity at pH 3.6. We need further, more detailed analysis to see the reason for such observations. However, at the moment we should mention that in these latter conditions, a large amount of Z chalcones were also formed. Because the reactions were conducted, I mean the incubations were kept in the dark, and preventing the light-initiated easy isomerization of the chalcones, the formation of the Z isomers, the only source of formation of the Z isomers is the retro-Michael reaction. In other words, it's elimination of the added N-acetylcysteine, regenerating the double bond. However, when this elimination occurs, Z chalcones can be formed, which from that time on are also can react with the thiol form, thiol form of N-acetylcysteine, whose stereochemistry and reactivity is not known at the moment. In other words, these observations need some further detailed analysis, mechanistic analysis of the reactions. And this chart will show the effects of the 6-membered ring chalcones on the reactivity. In this chart, we show the initial reactivity and the time course of the reaction of the methyl and methoxy substituted chalcones, I mean open chain chalcones, 1B and 1C, 1B and 1C. The 6-membered analogs, the tetralone chalcones, 2B and 2C, 2B and 2C, and the 7-membered analogs, 3B and 3C. What we can observe that the tetralone, I mean the six-membered analogs, okay, the reactivity of the six-membered analogs is somewhere between the open chain analogs, which react very fast, and the seven-membered analogs, which react much slowly. So this observation is important not only from theoretical point of view, however, from biological point of view as well. Namely, it means this experiment proved that changing the ring size of the cyclic chalcone analogs, we can fairly tune the tire reactivity of the compounds. And not only the ring size, but the substitution of the benzylidene moiety also affects the reactivity of the compounds towards diols. And systematically, the reactivity of the methyl derivatives, I mean the 1B, the 2B, and the 3B is always higher than the respective methoxy derivatives. So summarizing the experiments and give some conclusions, we could found that all the investigated chalcones and chalconoids, I mean cyclic chalcone analogs, showed spontaneous activity against the protonated and the deprotonated forms of reduced glutathione and N-acetylcysteine. Based on the initial reaction rates and equilibrium composition, the full methyl and methoxy substituted derivatives of series 1, open chalcones, and 4, seven-membered chalcone, the ring structure reduced the tire reactivity of the compounds. We interpreted the experiments with the difference between the electron density of the beta carbon atoms and the HOMO-LUMO energies of the chalcones and the thiols. In the reaction of derivatives 1, open chain chalcones, and N-acetylcysteine, under pH 2 acid conditions, remarkable diastereoselectivity was observed based on the HPLC-UV analysis. The observation was interpreted as formation of the cyclic transition product formed during the reactions. In the reaction of derivatives with 4, the seven-membered analogs, with GSH and NAC, formation of corresponding Z isomers was observed. The observation was interpreted with retro-Michael reaction. And the final conclusion that we can, by which I wish to close this unit, and at the same time, the whole series of this mini course, that the chalcone skeleton is a prosperous pharmacophore to design synthesis, development of covalent modifier type drug candidate. Such drug candidates are the number of such drug candidates are increasing and increasing and increasing. I gave an example with a very recent and good reviews on this type of compounds. For example, ibrutinib, which acts as a covalent modifier. So by this slide, I wish to close the whole series. I hope you found the content of this 6 lectures useful for your further studies, for your studies, for your research, for your master thesis or PhD thesis, and in case of interest and in case of further questions, you can turn me on anytime later of course, through email. So I will try to do my best and answer your questions which arisen in connection with these topics. Again, thank you very much for your attention. Thank you very much for the possibility of launching this mini course on chalcones.
Bon, finished our mini course. The professor Paul was, I think that was a good professor. Well, the conference was good. All I like to all, and I think that eu penso que todos vocês tenham tido uma experiência boa com este mini curso e que tenham conseguido, por lo menos, ter uma ideia de possibilidades de trabalho com chalconas e com outros compostos, também com outros tipos de e as possibilidades também de colaboração com a Universidade de Peixe, a qual nós estamos tentando, professor Paul, a mim e eu estamos tentando fazer uma colaboração instituída, é decir, fazer um convênio, colaboração com a universidade. Então, alguma pergunta? Alguém quer perguntar alguma coisa? Professor, thank you for your lecture. I was very excited with all of your speak here, and I think that we are going to do a lot of more work, and we are going to do a new working and a new collaboration. We continue our collaboration. Bom, alguma pergunta? Não tem pergunta para o professor? Estão dando obrigada por você, professor. The people is thank you for you, and it's very interesting because we are one people from Mozambique that was assisted your lectures. I don't know, but he's em Punana. Muito obrigada em Punana por você também estar presente em nosso curso. E esperamos vocês na próxima segunda-feira, às 13 horas, para o próximo seminário, o próximo seminário que será o seminário do Web Science do IQ. Até segunda. Thank you very much for all. Thank you very much for Professor.
Thank you.
We finish.